So for our second talk, I'm happy to welcome Barnabás Póczos here in our machine learning department. And he's going to be speaking about diffusion models for science, progress, challenges, and open questions.
Indeed, thank you. So indeed, my plan is to talk a little bit about diffusion models, the theory of diffusion models, show some applications that we did recently, and mention some open questions. And the reason for that, so my selfish reason is that I'm hoping that some of you might be interested and could help me answering some of those open questions that we are looking at right now. All right. So diffusion models, they belong to the part of generative AI methods, and they are these generative methods getting more and more popular, and there are many different versions. Here I just listed a few of them. Today I'm going to focus more on diffusion. And I will just very briefly review how they work. I know it was mentioned before. It's just my goal is just to be on the same page and discuss notation that we are going to use with that. So generally, the goal of generative AI methods is that we have a training set, x1, x2, xn, and they are coming IID from some distribution P, and the goal is to generate more data points xn plus 1, xn plus 2, xn plus m from the same distribution without ever estimating the density. So that's our goal. And sometimes we look at the conditional version of it, where we have a training data set, and the training data set comes in with labels xy pairs. So we have x1, y1, x2, y2, xn, yn, just like in regression. They are coming from some distribution P. And now for a new input y, our goal is to generate more new sample points, say xn plus 1, xn plus 2, xn plus m, from the conditional distribution of x given y. Again, without ever estimating the density. And so that's our goal. And just want to mention that these have been used in science applications for these generative AI methods for a long time. In 2017, we used variational outline encoder for generating galaxy images. And here you can see how they look like that time generated galaxy images. So on the left, those are simulated. On the right, those, sorry, the other way around. So these are the real images, and those are the generative AI generated images. And we asked scientists at that time already, we had this visual Turing test where scientists couldn't distinguish between generated galaxy images and real galaxy images. And after VAs, the next big movement was when GANs came out, and especially when it was demonstrated that with GANs we can generate these good quality face images. That was a big thing around that time. And then came diffusion, and now we say that GANs are so old school, we don't use them anymore that much. That said, in many applications, I still think that GANs could do very, very well. Just somehow people started to focus more on diffusion these days. All right, so I'm going to talk about diffusion, and just very quickly overview, just to be on the same page, discuss different directions that people study, and then I show some applications and then the open questions that I have. All right, so our goal is that we want to, first, we have we want to generate images. And then we have an image data set. In this case, I'm just showing one image from that. And first, we add some Gaussian noise iteratively to this image using this Markov chain that each time we add more and more Gaussian noise, still everything looks like very Gaussian. So we generate this forward Markov chain. And then we will try to do the reverse part of it, and starting from Gaussian noise, removing iteratively more and more noise, till we convert back to an image. It is a two-dimensional representation of the same thing. So, for example, we have this distribution, we add more and more Gaussian noise, till we convert to a distribution that looks like very Gaussian. And our goal is that iteratively just to go back and remove the noise. So that's the idea for denoising diffusion. So just to be a bit more formal, we start from some x0 image, And then we start adding more and more noise till we get to xt. That looks like a very Gaussian noise. And then our goal is to have a neural network that we denote with p theta, xt minus 1 xt, where the goal is that given xt, estimate what xt minus 1, but xt minus 1 was. And it turns out that if we add always a tiny bit more Gaussian noise, then this inverse process also closely looks like a Gaussian noise. And because of that, it's just enough to estimate the mean of that Gaussian noise and the variance of that Gaussian noise. So we want a neural network that from xt would estimate xt minus 1, and that estimation would be in this form, that the mean is denoted with this mu theta and the variance with that mu theta. So these are two neural networks. One is estimating the mean, the other is estimating the variance of the Gaussian noise. So just to visualize it, we want neural networks that look like this, that xt is the input, time is also an input, and the neural network would create estimation for the mean and the covariance of this Gaussian distribution that tries to simulate the inverse process. All right. One thing I wanted to mention that what kind of neural networks to use here, and that really depends on the application. On images, most often, or one of the most popular methods was UNet. That said, when we look at theory papers, I haven't seen investigating when people would use UNet and that would have any benefit over, say, fully connected neural networks. That said, in practice, I agree that UNet, when we tried, often on images, say UNet works much better than just fully connected neural networks. So it seems there's some gap in the theoretical understanding that how specialized neural networks could help when all the theory proof are about, say, ReLU neural networks and not about UNet structure. All right, so that's one idea. The other is using, so this was just using denoising. The other is using score functions. And the main idea here is that we have when we add more and more Gaussian noise, then we can, with that we create like a forward diffusion. And under some conditions, that forward diffusion can be inverted. That's called a backward diffusion. And then when we do it, then we can notice here that this term appears. That's called the score function. So if we could estimate that score from data, then we could just do that reverse diffusion very easily. So if we have a score estimation S hat, then we could just simulate this reverse process, and that would hopefully or ideally generate new images for us. So that's the second idea, using score instead of this previous approach that I mentioned with denoising. The problem is that score estimation is difficult. And I just want to mention that what saves us here is, that was mentioned in the previous talk as well, is this result from Vincent, which looks like this, that our goal, original goal is that we want to estimate the score, this quantity, the gradient of the log of the density at iteration t. This is what we want to estimate, but this is very difficult. However, if we condition on our starting point at 0, then we know that x condition on x0, x will be just Gaussian because that's how we created. We just added more and more Gaussian noise. So then we can calculate this in closed form. So this part is easy, this part is difficult. This is what we want. But the good thing is that it can be proved that for any s functions, what we want is just this guy plus a constant c. So if you want to minimize this, it's enough to minimize this. Because we know this guy, we don't know this guy, but these two objective functions only different with the additive constant c that doesn't depend on s. So it's like a beautiful save, and because of that we can do score estimation. Without that it wouldn't be possible, or wouldn't be that easy. All right. And the third idea I just want to mention that is using energy-based models, where we assume that the distribution, we have a parametric distribution family, and that's represented in this form where this E guy is the energy, and Z is a normalizing term. Often this normalizing term is very difficult to calculate in practice, but luckily, when we want to estimate the score, then that just disappears, so we don't need this guy anymore. So from the energy, we can get the score. And want to mention that if our goal is to generate samples from this distribution, and the energy is already known, then we have MCMC methods for that. When the score is known, then we have this score matching diffusion-based algorithms for that. So a new direction these days is combine these two things. So the idea is that you use the score-based diffusion, but if when you know the energy, then you can still use that energy-based MCMC methods to guide your diffusion. And in practice, that often works fine, and there are more and more papers coming out this direction, but in my opinion, the theory is still not quite understood that how much combination of these two things can help. All right, so these are the three directions, and now I would like to show some applications that what we did recently. And the first one I want to mention is we use diffusion, score-based diffusion to estimate galaxy cluster masses. And so this was the task. We had a data set, and from the data set, we wanted to estimate the gas and dark matter distribution of galaxy clusters. And our input to estimate, those were the Sanger-Zeldovich or SZ images and X-ray images. So those were our inputs. And conditionally on those inputs, our goal was to estimate the gas and dark matter distribution of galaxy clusters. And using this hyper simulation, we generated a large number of simulated galaxy clusters. In our data set, there were 34,000 simulated galaxy clusters. So these consist of the SZ image, the X-ray image, and we wanted to estimate the gas and dark matter distribution. And for the code, we used Alexander Adams' code from Lawrence's group. So, and this was great, so I recommend you that you should look at that too. And this is how our data instances look like. So our input was the SZ images and the X-ray images, and the output that we wanted to estimate is this map of gas and dark matter distribution. So from these, the goal was to estimate these. And we used score-based conditional diffusion for this, and the results looked pretty good. So I just wanted to show it here. So this was our input. We started from some Gaussian noise, and then during the reverse diffusion, we converged to the estimated dark matter and gas distributions. And just wanted to show some other results around this. So here you can see three sets of results. These are the inputs, the SZ and X-ray images. These are the true, so these two columns are the true gas distribution and dark matter distribution. And this is what we got as estimations using this score-based diffusion. This is for the gas distribution, and this is for the dark matter distribution. And the first row is just showing the predicted output scale between 0 and 1. And the bottom row just shows a logarithmic transformation after that to show a bit more structure of these images. And what you can see that diffusion estimated, so the dark matter distribution pretty well. So this image is pretty close to this. And similarly, the estimated gas distribution is pretty good, close to the simulated one too. All right, so this was one application in cosmology where score-based diffusion for generating more galaxy images worked pretty well. All right, the next application I want to show you is we call chemistry-inspired diffusion with non-differentiable guidance. So the problem is that in all these diffusion models that we discussed, those are purely data-driven. Here's a data set, generate more data points from that distribution. But they don't know anything about physics, or in chemistry problems, they don't know about chemistry either. So the question is, can we somehow extend these diffusion models with, say, chemistry or physics knowledge? And in our setting, the goal was we have a set of molecules, so that's our data set, and the goal was to generate more molecules that coming from that distribution. The problem again, that diffusion doesn't know anything about chemistry, but we also have some prior chemistry knowledge that, for example, we know the Schrödinger equation. So the question is, can we somehow guide the diffusion such that whatever they generate, they are compatible with the Schrödinger equation? So how to extend, how to change diffusion models such that whatever they generate, they agree with the physical or chemical laws. So that was the question. All right. So our goal was to generate 3D structure of molecules given a data set. And we also had an oracle that was able to estimate the energy, the potential energy of this molecule. Schrödinger equation generally calculating that it's very complicated, but there are some approximations using density functional theory. And we used one of those oracles that was able to generate those potential energy numbers. The goal is to generate stable molecules, meaning that has low potential energy after they are generated. The problem is that it's a simulation, right? So that whatever you generate, then you have to run these complicated calculations that calculates the energy levels. And that's not differentiable. So it's not that obvious how to extend diffusion models where we need differentiable neural networks with something that's not differentiable. So there are two ideas that you can do. One of them is that we can try to estimate the gradient of where the gradient is not available. And so other idea is that often people use that you train a neural network that would try to approximate your DFT calculations. And then because if we have this proxy neural network, you can calculate the gradient and you can combine things. So in this approach, you use the first one, where we just use some zeros order optimization methods that try to estimate the gradient and check if that's going to work. All right. So here is the setting. So in a molecule, we have n atoms, and we represent that molecule in this n times 3 plus d dimensional matrix. So each row belongs to an atom in the molecule. And the first 3 columns, those are just the 3-dimensional coordinates of the atom. And the last d coordinates, those describe the atoms. For example, it could be a one-hot code encoding of the atoms, or you can have some other features as well, like where they are in the periodic table or some other kind of features. So we have the molecules represented with this G matrix. So the first step that we did, that we embedded the molecules into a latent space. And for that embedding, we use variational encoder. So we are in this high-dimensional space. We embed everything to a latent space, and we try to do that embedding such a way that it could be invertible. So at the end, from that latent space, we are able to generate molecules. And then we are going to do the diffusion in this latent space. So we train the neural network that can just map these guys to a smaller dimensional space. In that smaller dimensional space, we will do the diffusion. And then from the smaller dimensional space, at the very end, when diffusion is done, we go back to the original space of the molecules. Another thing I wanted to mention that we did that in a way that this transformation kept the invariances and equivariances. That is, if we rotate the original molecule, a molecule in the original space, then the representation also rotates in the lower dimensional space. Similarly for translation as well. All right, so we have these variational autoencoders that can encode and decode molecules, and then we will use diffusion in this latent space. All right, so the next part of this project was to use our chemical knowledge, meaning that we have a molecule and on those atoms there are electrical forces. And we have our oracle that can calculate the potential energy or can calculate any forces on, can calculate the electrical forces on any atoms. And the molecule would be stable if you add all these forces on the atoms, and if that whatever you get, that's zero, then it means that the atoms wouldn't move. If the force is not zero, it means that the molecule is not stable, that atoms would move away. So we had this oracle that could calculate the forces, that is the differential of the energy with respect to the location. So, as I said, you could do that with Schrödinger equations, but that's very complicated. So typically people use some approximations, such as force field approximation or semi-empirical models or density functional theory-based methods. So in this case, we use this GFN to XTB-based methods. Again, it was, for now, what's important for us is that it can approximate the energy or the forces on the atoms in the molecule. All right. So now that we have that, the next question is, okay, what to do with our diffusion? How can we use that property? And this would be the equation for a denoising diffusion. So this guy is a neural network that tries to estimate the noise. And then after the neural network estimated the noise, then XT would be modified and you would generate a new XT minus one. And you would run this iteratively till you get to X0, and X0 would be ideally denoised, good-looking molecule. However, so that's just the original diffusion. But if you already have a quantity Y, and your goal is that to change the diffusion in such a way that it would encourage generation of those things that have this high value, then this is one way where people modify the original diffusion process with this extra term here. So this is called guided diffusion. And the main idea here is that you could train, say, a classifier or regression methods such that for any XT, it would estimate the corresponding Y value. And here ST is just how strong guidance we want on the diffusion. So in our case, for example, I denote with this F, our oracle, that can estimate for any molecule its energy level. Then we can choose this distribution to be just this, a normal distribution, would mean f of xt. So xt is our molecule, and f of xt is its calculated energy. And we just assume that this distribution is a normal distribution with that mean and with some noise. All right, and then you have this distribution, then you can plug that back here. All right, there are some challenges. The first challenge is that we start to generate the molecule from Gaussian noise. So you start from some Gaussian noise. And already on that Gaussian noise, to use this guidance, we should be able to tell that what will be the energy level of that molecule that we generate at the end. And that's just very difficult because everything just looks like a Gaussian noise at that point. So to overcome this difficulty, one approach that seems to work is that when you have xt, from that xt, you try to predict what would be x0, what you would get at the end of the diffusion. And that for that x0, you will use the oracle to estimate the energy level. So even in the intermediate steps, not just at the very end, when you are in the diffusion at xt, you would try to estimate very quickly what would be x0. For that x0, you will call the oracle to estimate the energy levels. All right, so I denote this transformation to T0, that again from xt, when you are at the T iteration of the diffusion, we just try to estimate what's the final final molecule would be, and then we call our oracle that can calculate the energy level of that molecule. All right, when we have that, then we can replace the guidance term here with this expression. All right, and the challenge number 2 is that our oracle is not differentiable, and here we need to calculate the gradient. So the question is what to do about that. So our idea was to use just the first, some empirical approximation of the gradient. So let this calligraphic f denote the composition of these functions. So T0 was that you are at you are doing your diffusion and you are at xt. From xt we try to estimate what's x0. That transformation is T0, and then we call the decoder of our original encoder to go back to the original molecule space. That's capital D. And then finally we call our oracle to calculate the energy level of that molecule. So all these function together, that's f. We don't know what's the gradient of this, but we can try to estimate. And one way to estimate is that wherever you are just add a small perturbation and you remove a small perturbation and divided this with the scale of your perturbation. And that's the estimated gradient. And the question is, okay, we don't know the gradient, we just estimated it. Will it work at all? And it turns out it works. So one lesson is that if you have a simulator and you want to use that simulator to guide your diffusion, and you might not know the derivative of your simulator, still numerical methods might still be good enough to guide your diffusion according to that simulator. All right, so I just want to show you some results about this, that this is the guidance scale, how strong guidance we used. And here are some metric about how good the generated molecules are. Here are some baselines that don't use any guidance, and the dark colors show the best methods, and all of them use some kind of guidance, and we got better results that way. And just to show some generated molecules as well, here without guidance, some molecules, and after we use guidance, then we got better results where the stability numbers improved. So these numbers show how stable the molecules are. The smaller, the better. And guidance where we used BFT or Schrödinger approximation that helped. And here are some more generated molecules on the QM9 data set and on the GEOM data sets where we have larger molecules as well. And many of them look quite reasonable. So the point here was that you can use some simulator-based guidance for your diffusion, and sometimes they help. All right, so back to my open questions. My first question that I quickly want to mention is on the convergence rates of diffusion-based models. So we assume that the distribution belongs to a Hölder function class. And then we can prove that if you use diffusion, this is the true conditional distribution. This is the distribution what you would get with diffusion after doing the reverse diffusion to T0 step. And this is the convergence rate we can get. If you look at this, the beta is your Hölder function class parameter. D is the dimensionality of your X, and D is the dimensionality of your Y. So we are doing conditional diffusion. And this, we can prove that this is a convergence rate that we get for diffusion, and T is just the total variation distance between the estimated distribution and the true distribution. If we use a bit stronger assumptions, then we can get this kind of convergence rate where this 4 disappears and it looks like that. And we can also prove that this is minimax optimal. But if you look at it, it also suffers from the curse of dimensionality very badly here. So on one hand, we can prove that if we assume beta Hölder distributions, then we can calculate the convergence rate of diffusion, and that will be minimax optimal. In some sense, you cannot even do better. At the same time, GANs also get the same kind of convergence rate. So it seems GANs and diffusion, they have the same convergence rate. In practice, however, diffusion works much better than these rates. And the question is, why is that? And one reason could be that the function family that we started with, where we are just assuming that the distributions are Hölder continuous, is just not the best approximation for best assumption in practice. People calculated convergence rate and they assume best of function class, suffer from the curse of dimensionality there as well. So something is still missing here. All right, so that's question number 1. Another question I want to mention, that we always use neural networks in diffusion, but technically they are not needed, because all we need is just to have a regression method that from x minus 1 it will predict xt. And we use neural networks, but that's really not needed. You could replace this part with XGBoost, support vector measurements, k-nearest neighbor case regression, local polynomial regression, whatever you want. And you could get a diffusion that wouldn't use neural networks, it would use some other kind of approaches. And we know some applications that say XGBoost works better than neural networks, and maybe there could be some applications where, forgetting about neural networks, you could get a diffusion-based methods that work better than the neural network-based approaches. And so the question could be that, what would be the convergence rate of these new diffusion-based methods that wouldn't use neural networks, but would use, say, XGBoost or other kind of regression methods? And the next question is that now we could use these models to generate more complicated objects. Because, so originally this diffusion, how it's described, it's just, it can generate only vector objects from a distribution. So you have a distribution in a finite dimensional vectorial space, and we try to generate more samples from that distribution. But what if my goal is to generate graphs, or generate functions, or generate point clouds, or other kind of things? Then if you think of this, there are many different methods that can, regression methods that can do that. Like, for example, there are regression methods of graph, where X is a graph, X minus is a graph, and we could use those as well. Some of them are neural network-based, some of them are not. But the point is that way we could use diffusion to generate more complicated objects, not just vectors. And how many minutes I have left? 1 minute. Okay, so the final one. So for example, if you look at images, an image, you can think of this, say it's 100 times 100 dimensional image, then it has 10,000 dimensions. If I scale this image up to 1,000 by 1,000, it has 1 million images, 1 million dimension. And all this theory would say that you suffer very badly from the curse of dimensionality, it's not good. But we know that that's just weird. It's not what happens when if I enlarge an image from 100 to 1,000 by 1,000, I shouldn't suffer that much from the curse of dimensionality. So maybe a better way would be that instead of thinking an image that's a 100 times 100 dimensional vector, think of this as a 2-dimensional function. So an image is a 2-dimensional functions that maps to RGB scores. So that's an image. And then we need diffusion-based methods that will generate functions instead of vectors or matrices. And how could we do it? One way is that you could replace this Gaussian, finite dimensional Gaussian noise with the Gaussian process. And then xt would be a function instead of a vector. So xt at location u would be the previous xt minus 1 at location u plus a Gaussian process noise. And the goal is just to reverse this thing. So then what do we need? We need, for this regression, xt minus 1 is a function, xt is a function. Similarly here, xt minus 1 is a function, x is a function. So we just need a function-to-function regression. But there are approaches for that. There are neural network-based approaches and non-neural network-based approaches as well. And both could be studied, and we could get convergence rates for these kind of approaches too. All right. So I have many more questions, but I start another time.
What we started a couple of minutes late. So if you have a question, please. Oh.
Yep. So just one more there. Thank you. So the next one is related to how can we generate more complicated objects. For example, if the goal is to generate a point cloud. So we developed a GAN-based point cloud generation, but there are diffusion-based point cloud generation algorithms as well. And here it's like a hierarchical generation process, because first you decide what kind of objects you want to generate. And then when you decide it, then you can generate points from the corresponding three-dimensional distribution of that object. Right? So first, you have a theta. The theta decides you want to generate an airplane or a base or a chair. And then when you condition on that, then each theta defines a new three-dimensional distribution, and you try to generate more points from those three-dimensional distributions. So that's how they work. So in this case, it's a hierarchical structure for diffusion. And the trick is that at some point, when you started to generate some points, you look at that set. From that set, you should be able to predict what kind of objects you already generated. So now your input is a set, and the output should be what kind of objects we are working to generate. So we need neural network that can take set as an input and predict a class label what kind of objects we are generating. But luckily, there are neural networks like that. One of them we developed is called DeepSet that can do that too. And that can be plugged into these diffusion models to create point cloud GAN generation or point cloud diffusion generation. Okay, so we have algorithms. We don't have convergence rates, but I think that could be done too, to calculate convergence rates of point cloud based diffusion as well. All right, so I stop here and thanks for your attention. If you are interested in these open questions, please talk to me and I would be happy to discuss the details with you. Thank you.